All right, we're going to do a little bit change of pace here. My hands are no longer in view, but you can see what they're doing through this mouse here. We're going to talk a little bit about Matlab. So Matlab stands for Matrix Laboratory, in case you weren't aware. And so it is designed to make doing all of the operations that we've learned about in linear algebra so far as simple as possible. And so really, if you just think in terms of matrices, you'll understand pretty much all of the MATLAB syntax and how to make it work. So what we're going to do first is we're going to just talk a little bit about the operations that we've done so far. So how would you define a vector? How would you define a matrix? How do you do matrix multiplication? How would you compute norms and dot products and eigenvalues, that sort of thing? Just a brief overview so that we can begin to use some of its functionality in future lectures. So here we have the command window, which is just like a little prompt at which you can type any command that you want. You can store quantities in variables that will show up in the workspace, and these variables are all vector or matrix quantities. Actually, to be more precise, they could be arbitrary tensors, so they can have any sort of dimensions. So let's start with something simple. Let's define a number. So if I type in r equals 2, this expression says that I want to assign the value 2 to the variable named r. So when I hit enter, it tells me r equals 2, and over here I can see the name r, value 2. Now, how do we make vectors? Let's make a vector v. So I say v equals left bracket. I type in the first component, and then I'm making a column vector, so for columns I use semicolons. So that's one way to remember it. Okay, I'm making this up as I go. Sorry, -1. Close it with a right bracket, hit enter. So v is a 5-dimensional vector. If I wanted to make a row vector, I do, I'll call it w equals, I do number, and then for row vectors I use a comma. 5, 4, 6, 8. Great. All right. Now, any mathematical expression I type in here, MATLAB will interpret as a matrix equation. So if I try to do, remember matrix multiplication, if I try to do v times w, then since v is 5 by 1 and w is 1 by 5, I will get a 5 by 5 matrix. And this is the tensor product of these two vectors. If I do w times v, this is going to be a 1 by 5 times a 5 by 1, so this will give me a 1 by 5. This will give me a 1 by 1, so this will be the dot product of vectors, 12. Okay? If I try to do v times v, which won't work because we've got a 5 by 1 and a 5 by 1, it's going to give me an error. Inner matrix dimensions must agree. So that comes from the properties of matrix multiplication. So to clear the screen, I just type clear. Actually, that cleared all my variables. It's been a while since I've used this, so just clear the screen, use CLC. Let's do some dot products. So I'll define a vector, v equals, and it's going to be a column vector. I'm going to be 1, -1, 2. And remember, the formula for the dot product is, well, MATLAB has a command. You can just type dot, v and v. It's going to give me 6. Or I can do v transpose v. And in MATLAB, v transpose, the transpose of a matrix is given by this apostrophe. So that means v transpose, if I hit this, I get a row vector. So v transpose times v is going to give me 6. Okay? So if I want to do the norm of v, I can type norm v. It's going to give me square root of 6, which I can check. Yep. Or I could do square root of v transpose times v. Gives me the same answer. Let's do some matrix multiplications. I'll define a matrix, and it's going to be 3 by 3. So I'll do 1, this is going to be the top row, 2, 3. minus 3, 2, 1, 8, 1, 2. So what I've done here is I've done the row 1, and then the semicolon means move down to the next column, or next row, and then finally the final row. I hit this, gives it back to me. So if I do v times a, so a is 3 by 3, v is 3 by 1, or 3 by 1, so if I do a times v, I'm going to get a 3 by 1 vector out, and that's a acting on v. Okay? If I do v transpose times a, it's going to give me it's going to give me a row vector, but, nope, CLC. If I wanted to do, so what we learned in the third problem set, if you do, well, I guess you are supposed to be doing this at the moment, but if I do a times v transpose, and then I do v transpose times a transpose, check that out. I can multiply matrices together, so if I give another 3 by 3 matrix, 3, 2, 1, minus 1, minus 1, minus 1, oops, sorry, and give me some numbers, 7, 6, 8, 4, 2, or 2, 3, 2, 3, 1, 5, 1, 4, 3, I'm being ridiculous here, so minus 9, a lot of zeros, whatever. There's my matrix. I can do b times a. Great. I can do a times b, and notice that they're different, because b times a is not equal to a times b. All right. Now, we've done dot products, we've done norms. So how would you do a projection? Let's do the Gram-Schmidt problem in Matlab. I gotta look it up. Okay, the first thing that we need to do is make sure that we've cleared everything out. Then we're going to define our vectors. So v1 was a column vector, 0, 0, 3. Sorry. v2, also a column vector, was minus 5, 7, 13. Minus 5, 7, 13. v3 was something ridiculous, 4, 8, minus 2. Whoops. Okay, so Gram-Schmidt, the first thing we do is we define E1 to be V1 divided by the length of V1. And we know the length of V1, or the norm of V1, is square root of V1 transpose times V1. And there it is. So that's E1. That's our first basis vector, not orthonormal basis. Now, what we'll do is we'll define E2 to be V2 minus the projection of V2 onto E1. So how do we do that projection? Well, we dot V2 with E1. Okay? Now, this is not normalized. So if I do norm of E2, I should get, which should be oh, I know what I did wrong. So, sorry about that. When I went up here, E2 is going to be V2 minus dot V2 E1. This is just a number times E1. There we go. So now norm of E2 is going to be square root of 74. So we can do E2, we can normalize E2 by doing E2 equals E2 divided by norm of E2. Okay. And now finally for our last vector, we do E3 equals v3 minus dot v3 e1 times e1 minus dot v3 e2 times e2. And this is also not normalized, so then we have to normalize it. So we do e3 equals e3 divided by norm e3. And there you go. So we have our orthonormal basis, e1, e2, e3. Let's check if they're orthonormal. So first we'll check normality. Norm of e1 is 1. Norm e2 is 1. Norm e3 is 1. Let's check orthogonality. So dot e1, e2 should be 0. Lo and behold. Dot e2, e3. Okay, so since MATLAB is a numerical software program, everything it does is, since computers are only work in integers and you're trying to represent real numbers with integers or discrete quantities, there's a lot of round-off error. Well, not a lot, but there's the existence of round-off error. So this is minus 5.5 times 10 to the negative 17th. This is, in MATLAB language, 0. This is pretty much the same as 0. So the dot product is 0. It has to do with rounding off. And then finally, dot e1, e3, 0. So these vectors are all orthogonal to each other, and we have an orthonormal basis. Okay, let's do some eigenvector work. Starting over. All right, so if I define a matrix, let's do 3 by 3 again. 3 minus 2, 1, or I gotta be more creative. 13. That's a sucky number. Minus 3.2, 4, round numbers, 100. 2, 2, 2. There's my matrix. Fantastic. If I do eig of A, it's going to give me the eigenvalues. But that's not great. I mean, I want the eigenvectors as well as the eigenvalues. So what I have to do is I have to set VW equal to eig A. And it will, oh, sorry, I am not used to using MATLAB, honestly. There we go. Okay, so what has happened here? V is going to be our eigenvectors. Each one of these is an eigenvector. And W is going to be our diagonal matrix of eigenvalues. So you can see the eigenvalues here. So the first eigenvalue here corresponds to this eigenvalue. This corresponds to this eigenvalue. This vector. This corresponds to this eigenvector.